Okay, good afternoon. Once again, I hope we are all fine. I'm going to request someone to put up their hand such that we can request them to unmute and they lead us in a word of prayer before we begin. Anyone to lead us in a word of prayer? Ashley? Sasha, please pray for us and let's begin.
Let us pray. Mighty Father, we thank you for this day. We thank you for enabling us come into this lesson. Please be with us throughout it. Help us understand everything that we are going to be taught. Let us exit the lesson when we have learned something. In Jesus' name I've prayed. Amen.
Thank you, Sasha. So, before we go into our lesson, as our norm is, we are going to share a devotion. This devotion says, "Get fired up." Psalms 39, verse 3. My heart was hot within me while I was musing. The fire burned, then I spoke with my tongue. Have you ever been so excited about something that you couldn't keep it to yourself? That's how it feels when God's word fills your heart. It sets a fire inside you. You become so full of joy and passion that you cannot stay quiet about it. In the Bible, Prophet Jeremiah said he didn't want to talk about God anymore, but God's word was like a fire shut up in his bones. He couldn't keep silent. He had to speak. When you read Jeremiah 20, verse 9, the same fire comes alive in you when you study God's word. As you meditate on it and speak it to yourself, you become bolder, more joyful, and full of God's power to share his love with more people. So go ahead and get fired up. You can kindly take on the prayer. I am passionate about preaching the gospel. God's word burns in my heart, and I boldly tell everyone about God's love everywhere. In Jesus' name, amen. Thank you for listening. So, we are going to continue from where we stopped. I remember I gave us an assignment, and I think only 2 people shared what they were able to get. I don't know what happened to the rest of us, but it's always important that when we are given an assignment, we endeavor to share such that we can be guided. Because one of the people that shared, I hope they are here, because you realize I said use colored flowers. Of course, how substances change the colors, but realize that when you use colored substances, you acknowledge the fact that the colored flowers or the colored leaves have the what? The flavin that we said is responsible for the color changes in different pH media. So it's important that we take note of some of those things. And I don't know who else actually did that work, but at least for the 2 people that did, kudos. The rest of us, I believe we can do better than that. Okay, so people who keep writing on the screen, it's bad manners to do so. So please hold your device well. And of course, we had answered these questions I think we had said we would answer them after you have done the assignment. So I think we can go through these questions and we can join into what we have to study today. So, Sasha, you will help me unmute those people that will be putting up their hands. So our first question here is asking, why is ethanol or propanol used in the preparation of the extract? Because remember, if we could slightly go back to the previous slide, I would request someone to put up their hands such that they read for us this procedure, such that we can be able to align with the questions that we have. Yes, Sasha, but I think going forward we should have someone else. But you can read for now since we want to beat time.
Obtaining an indicator from plant extracts. Cut as many petals as possible from one type of flower into small pieces. Grind as many petals as possible in a mortar using a pestle to obtain a paste. Measure 5 centimeters cubed of ethanol or propanol or warm water and continue grinding until a deep color of the flower extract appears. Sieve the mixture and cover it. Get your different substances to be tested as alkaline or acidic.
Okay, thank you so much. That was good. So I think we can pick a leaf from here. When you look at pointer 4, it says measure 5 centimeters cubed of ethanol or propanol or warm water. So that means we are using any of these three. So if you don't have ethanol, you could use propanol. If you don't have propanol, you don't say, banange, me, I want to do that assignment. You go and get water that is warm or even hot water. You ensure that it gets warm and then you're able to add it to your what? To your mixture. So it's important that we carried out that experiment. Please mute if you're not chosen to speak. Okay, so we have a question here saying, why is ethanol or propanol used in preparation of the extract? Why do we use ethanol or propanol? Sasha, please mute your mic. Only unmute if you're giving an answer. Thank you. So why is ethanol or propanol used in the preparation of the extract? I've seen some answer in the chat. Ethanol, propanol dissolve the substance responsible for coloring. Okay, that is good. Jeremiah and Jamie, please use the chat for answers because I don't want to open and find their sticky notes and funny comments. Let's stick to what? To the cause of this lesson. Otherwise, I'll be forced to restrict the chat. So let's pay attention and use the chat for productive work. Okay, so the answer that has been posted in the chat is very true. Ethanol and propanol dissolved substances responsible for coloring. And then why do we use colored flowers? Why don't we use any flower that we find? Why do we use only colored flowers? Because if you can remember in our lesson last week, we said we use morning glory, hibiscus, purple red cabbages, and then we can also use the red bougainvillea. So why do we use colored flowers? Senior twos, please put up your hands. It's very important to participate in class. Some people are very active in posting in the chat, but when it comes to these other things, they are also on their other things. Einstein, I don't understand your answer. Can you elaborate more? Because I don't understand when you say indicators. Why do we use colored flowers? I remember we shared about this slide last week. Patricia says it's her first time in this lesson. Follow up, and where you have answers, you can as well put up your hand and respond. I was asking which topic. We are looking at alkalis and acids and alkalis. Okay, so I remember last time I told us that we use colored flowers because they have a component called flavin. And flavin is responsible for changing color in the different pH media. Because I said if we have an acid, for example, we said, those that can remember, we said for raw mangoes, the acidity level is higher than when you look at the ripe mangoes. So that means when a mango ripens, it's not that it has lost its acidity, but the level of acidity reduces. So that means when you use these colored indicators, you're going to notice that uh, the raw mango is going to give you a different color, and the ripe mango juice is also going to give you a different color when you add that indicator. But even with that, you're going to find that both colors belong to the acidic range. But you'll find that the one for the raw mango, the acidic range is higher compared to the one that is ripe. So you have to always remember that the only reason why we use those colored flowers is because of that component called flavin. So it's important to take note of that. Okay, so those people sending themselves highs, you've left me with no other option apart from me closing the chat. So if you have any response, you either send it to me or to the host. She will be sharing with me if you shared answers there. God love, it's okay if this is your first lesson. We have so far, I think, one lesson recorded because last week we weren't able to have our lesson because of the internet shortage. So that means you're going to go to the YouTube channel and you will watch the first lesson that we had. Just type in Senior 2 Holistic E-Learning Platform Chemistry lesson. It will actually bring you all the different YouTube videos. So you look for the one for January 2026. It was only one, maybe plus today's lesson, there will be two. So if it's your first lesson, just follow through because we covered a whole lot in the first lesson. It will be hard for us to go back to the previous slides, but just ensure that you're able to learn. Okay, so why do we use colored flowers? I've explained that. So we've said, we use colored flowers because they have flavin, which is a special molecule which has the ability to change its color when added to solutions of different pH. So that is important to really note. Then why do we cover the solution after sieving? You can put up your hand and share, or you can share your answer in the chat. Why do we cover the solution after sieving? Let's hear from Queen. Dilda, is your hand up or what? Sorry.
Good afternoon, madam.
Good afternoon, Queen.
I think why we cover the solution after sieving, I think it's because to prevent any like germs or other stuff from entering.
Okay, thank you. That is good. Anyone else? Sasha, do you have some answers in the chat? Dilda?
Yes.
What answers are people giving you?
To prevent ethanol from evaporating, to prevent it from contamination, prevent the ethanol from evaporating, and that's all.
Okay, thank you for those that have responded. Oshaka?
Uh, Teacher, may I think
Hey, did we lose you? Because I didn't hear anything. I just heard teacher we use, and that's all. Okay, anyway, I think we said that we cover it to prevent the ethanol from escaping, because we said if you leave it there, you're going to find when the ethanol has escaped, and that means your concentration will have lost its ability to make the definite changes in the colors that we are really hoping for. Okay, so what is the importance of grinding the colored petals? What is the importance of grinding the colored petals? Share your answers in the chat, or you can put up your hand. What is the importance of grinding the colored petals? Gilda? Sasha, do you have any answers in the chat?
Not yet.
To maximize the release of pigments and active compounds by breaking down the cellular structure that remains intact even after initial sorting.
Okay, thank you. So basically, the primary reason of grinding those petals is for us to extract the fluid. Because remember, even while we are adding the ethanol, the fluid that we are getting from these petals, that colored fluid, is what is actually very important. So that means in that case, it becomes easy to extract out the what? The juice from the petals. Then Jeremiah in the chat is saying to extract the dye or pigment easily into the solution. That is very true. Okay, so with that said, let's move on. Thank you for those that are really giving it their best to contribute answers. So the test of the different indicators. So I had given us an assignment and I told us to use those substances. I don't know what we found out and what colors they turn to, but that was your work to find out depending on which leaves you have used. Can we have anyone who tried out that experiment to tell us what their experience was as they carried it out? And I've
The tea leaves turn yellow.
Okay, so sorry I had gone off and I hadn't realized. But like I was saying, that are there people that tried out that experiment and they would want to share with us what they found out? What were your experiences like as you carried out that experiment?
Unfortunately, I didn't carry out the experiment, but I would like to send you some data so that you can be with us and teach us more of your knowledge.
Okay, so as I was saying, I don't know why my network is a bit unstable. You'll forgive me for that. As I was saying, we have different indicators. And those different indicators, like I told you, the one you prepared was your natural indicator. So like I said, you don't look stranded and you say, hey, me, I don't know what to do. There is always a way out. If you can't use the what, if you can't attain the commercial indicators, then you can as well use the what? The natural indicator. So indicators change color depending on the medium in which they are exposed, and there are different other indicators which are commercial. Can we share some of the indicators that we know? Maybe you've been in the lab and you've seen some of these indicators, or maybe you've read about them. Please share on some of those indicators if there are any that you know. Feel free to check to share in the chat and also put up your hand. Aimal,
This teacher is a universal indicator.
very good. We have the universal indicator. Any other? Yes, Chantel.
Litmus paper.
Litmus paper, very good. Jeremiah says litmus paper. Okay. So we have also others, such as seeing Mita Orange, Ivan, Then Jeremiah methyl red. Okay, that is good. Any others? Yes, Aimal. Okay, so
Miss Light, I was asking if you could send me a number and I send you data so that you can give us your knowledge without going on.
so we have phenolphthalein. So phenolphthalein is another indicator that we have. So we have litmus paper, we have methyl orange, we have phenolphthalein indicator, we have universal indicator, and we have the litmus solution. And you notice that in our lesson last week, we looked at how litmus paper changes in different media. And we said that if you place blue litmus paper we have alkali and base, and then we also have acids. So when you have a blue litmus paper, we said blue litmus paper remains blue with an alkali, then it turns red with acids. Then when we have red litmus paper, it turns blue in an alkali and remains red in an acid. So what does that mean? We have those slips of papers in the lab. They are colored red and blue, and they're the ones we call litmus papers. So we use them to test whether that substance is an alkali or an acid. I remember in last week's lesson, I told people that you can be free to test lemons and you say, oh, this lemon is sour. And then you're able to know that it's acidic. Then you can test soap and you notice that soap is bitter and slippery. And you will be okay except when you take it in huge amounts. And you will say it's an alkali. But when it comes to the lab, don't catch yourself testing those reagents there. So that means when we get the hydrochloric acid, we don't expect you to start touching it with your hands. Oh, the teacher on Zoom told us that we should touch and feel. If you touch it, you'll lose your fingers. If you test, you'll lose your tongue or even the whole face. So it's important that we have these different indicators in order to test whether the substance is alkali or acidic without us having to test with our lips, without us having to touch those fluids. So that's why we say that when you use blue litmus paper on an alkali, it's going to remain blue. And then when you use it on an acid, it's going to turn red. Then for the red litmus paper, when you use it in an alkali, it's going to turn blue, and in an acid, it's going to remain red. So it's important that you take note of that summary. Okay, so the color changes that occur, I just have a small summary here, and of course we are going to watch a video on how the universal indicator changes the color of those different substances. So we have name of the indicator, we have litmus paper, and the color in acidic solution is that the blue litmus paper turns red. And then we also have in alkaline solution, the red litmus paper turns blue. Then we have in methyl orange is orange, like the way you hear methyl orange. So that means its color is orange. So in an acidic solution, it turns red, and in an alkali solution, it turns yellow. Then when we are using phenolphthalein, phenolphthalein is colorless. So phenolphthalein remains colorless in an acidic media, while in an alkaline media, it turns to pink. So those are some of the changes that occur when we use these different indicators. And it's very important to take note of that. Yes, Samsung. And please use your names because it sounds funny calling you Samsung.
Okay, I'll put my name later, but at the moment, why does phenolphthalein turn colorless?
It doesn't turn colorless, it remains colorless. Phenolphthalein itself is a colorless solution. So when exposed to an acidic media, it remains colorless. There is no change. So that's how you will know that I'm working with an acid. If you add phenolphthalein to an acid, it will remain the same way it was. But when you add
Okay,
it to an alkaline, it's going to turn to pink.
that's nice. Okay, thank you for that.
You're welcome. But please put your name. Okay, people are here asking, what about turmeric? What about litmus solution? What about wood ash? All these could work as indicators, but like I said, some of these are restricted to the fact that they belong to a certain category. They are either acidic or alkaline. So using them as indicators minimizes our level of obtaining our desired product at the end of the day. Yes, Donald? Okay, so the strength of acids and alkalis. So let's get someone to raise their hand and they read for us this statement. Kian, Kian, please unmute and read for us. Okay, let's hear from Patricia.
Strength of acids and alkalis. It is safe to test lemon juice, but it's not to test sulfuric acid found in car batteries.
Okay, thank you. That is good. So, like I said, you find that some of these acids are eatable, but then there are those that you're not going to test. For example, you're not going to go to the car battery and you say, let me start testing the sulfuric acid there. It will deal with you graciously. So that means in that case, we need to find strategies. How do we find the degree or the difference between the acidity of sulfuric acid and that of lemon juice? Because definitely the one for sulfuric acid is much higher than the one in lemon juice. So how are we going to know? Like, for example, the example that I gave you, that if you have a raw mango and a ripe mango, you're going to get different colors, but both these mangoes are acidic. But there is a difference. The one that is ripe is less acidic, yet the one that is raw is more acidic. So basically, the degree of acidity changes, but how are we going to know the degree of acidity? So that means we have strong and weak acids. So the strong acids and weak acids are different. So when we look at sulfuric acid falls under the strong acids, while the citric acid, because it's the one we find in lemon juice, because They may ask someone an example of an acid and they put lemon juice. They'll cross you. So you talk about the acid in the lemon juice, which is citric acid, which some of you call citric. So that means we have a strong acid, which is sulfuric acid, and then we also have the citric acid. So I just want us to watch this video before we can proceed. Then I can clarify more on some things.
In this experiment, we're going to look at the reaction of acids and alkalis with universal indicator. I'm also going to add a marble chip to see if we get any reaction. So first of all, we're going to take 5 ml of each solution and pop it into a test tube. So our first solution today is hydrochloric acid. I'm then going to use citric acid. Our next one is ethanoic acid. The next solution is distilled water. And then we have ammonia. Sodium hydrogen carbonate. And our last one is sodium hydroxide. Into each test tube, I'm going to add a few drops of our universal indicator. And we'll then gently mix the test tubes. So our first one was hydrochloric acid. And then we had citric acid. And then ethanoic acid. Distilled water. Ammonia. sodium hydrogen carbonate. And sodium hydroxide. So at this side, we can see these are all acidic. And at this side, we can see our alkalis. Next, I'm going to add some marble chips into each test tube and see if we get any reaction. So first of all, we're going to take 5 ml.
So here you're going to notice that this lady is trying out the universal indicator on different on different substances to find out whether they are acidic or alkaline. So when you look at the universal indicator is this one here with the red topper on it. So it's green in color. Then we have the different substances here. The first one here is hydrochloric acid. The next one is citric acid. The next one is ethanoic acid. The next one is distilled water. The next one is ammonia. The next one is sodium hydrogen carbonate. The next one is sodium hydroxide. So you're going to notice something, that when she added the universal indicator to the hydrochloric acid, which was the first test tube here, it turned to pink. So when you look at her chart here, this chart that has pH 1, pH 3, pH 5, where she placed the bottle with the universal indicator, you notice that if we have pink, that means that substance has a pH of 1. So when you look at citric acid or citric acid, you find that it has also that pinkish color, but you realize that its pink is darker than the hydrochloric acid. That means the citric acid, for it's less acidic, but still highly acidic. Then when you look at the ethanoic acid, still you find that the color is different from these other two. That means for it's a weaker acid. Then when you look at the distilled water was green. Reason being, water is neutral. It's neither acidic or alkaline. So that means it will take on the color of the universal indicator. So that's why you realize that it was green. Then when you look at ammonia had that pale green. So the pale green shows that it's a weak acid. Sorry, it's a weak alkali. And then when you look at the sodium hydrogen carbonate, still you realize that it was bluish. That shows that it is an alkali as well. But at that point, it is more alkaline than the ammonia. Then when you look at sodium hydroxide, it had that deep blue solution. So just imagine the indicator turned from green to deep blue. So that means in that case, the sodium hydroxide is a strong alkali. That means it has a higher pH. Of course, I'm going to draw for us the pH scale and describe some of the few components there, but I wanted you to see what color changes take place if we have different pHs. So I'm going to play this again, but I wanted to first echo out what is being done, such that the second time I'm playing it, you're taking down notes and you're understanding what is going on.
Of each solution and pop it into a test tube. So our first solution today is hydrochloric acid. I'm then going to use citric acid. Our next one is ethanoic acid. The next solution is distilled water. And then we have ammonia. Sodium hydrogen carbonate. And our last one is sodium hydroxide. Into each test tube, I'm going to add a few drops of our universal indicator. And we'll then gently mix the test tubes. So our first one was hydrochloric acid. And then we had citric acid. And then ethanoic acid. Distilled water. Ammonia. Sodium hydrogen carbonate. And sodium hydroxide. So at this side we can see these are all acidic, and at this side we can see our alkalis. Next, I'm going to add some marble chips into each test tube and see if we get any reaction.
Are you cramming for a big biology test? Then you need to look at this right now. All you need to do is go to flexia.org, type your question.
In this nugget, we will be discussing universal indicators. Acids and bases are chemicals that can be found in everyday materials, such as citrus fruits and toothpaste. When an acid is dissolved in water, we get an acidic solution, such as hydrochloric acid. When an alkali is dissolved in water, we get an alkaline solution, such as sodium hydroxide. If a solution is neither acidic nor alkaline, it is neutral, such as water. But how do we find out a solution's pH? To find out, you can use an indicator. Indicators are substances that change colour when they are added to acidic, alkaline or neutral solutions. Universal indicator is a wide-range indicator made up of a mixture of several different indicators. It comes in the form of a solution or paper. Universal indicator can give an approximate value for pH using a colour chart matched with specific pH numbers from pH 0 to pH 14. Solutions with a pH below 7 are acidic. Solutions with a pH above 7 are alkaline. And solutions with a pH of 7 are neutral. The closer to pH 0, the more acidic a solution is. The closer to pH 14, the more alkaline a solution is. Universal indicator is very versatile because it can show us how acidic or alkaline a solution is. The universal indicator colour chart corresponds with pH numbers, so it can help us to estimate the pH of a solution. A few drops are added to the solution, and the colour is matched with the colour chart, which indicates the approximate pH. If the solution turns red, it has a pH of 0, so is very acidic. If the solution turns green, it has a pH of 7, so it is neutral. Universal indicator paper works in a similar way. A clean glass rod is dipped into the solution, and 1 drop of solution is transferred to a piece of universal indicator paper on a white tile. After a short period of time, a colour will develop, which can be matched to the colour chart. Here, the paper has turned dark blue, which means the solution is alkaline because it has a pH of 11. Universal indicator colours vary slightly between manufacturer, so colour charts are usually provided by them. Summary. The pH scale is used to measure whether a solution is acidic, alkaline or neutral. Indicators are dyes that change colour when added to acidic, alkaline or neutral solutions. Universal indicator is a wide-range indicator that can tell us how acidic or alkaline a substance is. Solutions are more acidic if they are closer to pH 0 and more alkaline if they are closer to pH 14. pH 7 is neutral. Each pH number has a specific colour. This means that universal indicator can help us to estimate the pH of a solution. Keywords. Acid, a solution with a pH less than 7. Alkali, a solution with a pH more than 7. Indicator, a substance used to determine if a solution is acidic or alkaline. Neutral, a solution with a pH of 7. pH scale, a scale to show how acidic, alkaline or neutral a solution is. An acid has a pH between 0 and 6. An alkali has a pH between 8 and 14, and neutral solutions have a pH of 7. Universal indicator, a type of indicator that can tell how acidic or alkaline a solution is. In this nugget, we will be discussing universal indicators. Acids and bases are chemicals that can be found in everyday materials, such as citrus fruits and toothpaste. When an acid is dissolved in water, we get an acidic solution, such as hydrochloric acid. When an alkali is dissolved in water, we get an alkaline solution, such as sodium hydroxide. If a solution is neither acidic nor alkaline, it is neutral, such as water. But how do we find out a solution's pH? To find out, you can use an indicator. Indicators are substances that change colour when they are added to acidic, alkaline or neutral solutions. Universal indicator is a wide-range indicator made up of a mixture of several different indicators. It comes in the form of a solution or paper. Universal indicator can give an approximate value for pH using a colour chart matched with specific pH numbers from pH 0 to pH 14. Solutions with a pH below 7 are acidic. Solutions with a pH above 7 are alkaline. And solutions with a pH of 7 are neutral.
And so here, I just want to clarify something before we move on. When you look at the different colors, you're going to notice that we have the different sets of colors ranging from 0 to 6, and then 7, and then from 8 to 14. When we have pH scale, it runs from 0 to 14. But basically, we usually consider 1 to 14. So that means from between 1 to 6, we have an acidic medium, and 7 is the neutral, then 8 to 14 is alkaline. But the difference here is, when you look at the one on the acidic scale, 1 is more acidic than 6. 1 is more acidic than 5. 1 is more acidic than 4. 1 is more acidic than 3. 1 is more acidic than 2. So that means, I don't know how your gadget is, but as I am teaching, my 1 is on my left hand. So that means the more I go to the left, the higher the acidity of that given substance. So that means when I add my universal indicator to a given solution and I get any of these colors, I can be able to tell that this is the pH of this solution. And not only just saying it's acidic, but also knowing whether it is highly acidic or moderately acidic or low acidity. Then for neutral, for it, it's always green, and its green is more like the same color with the universal indicator. Then for the alkaline, still the way I am sitting, my 8 is on my left hand and my 14 is on my right hand. That means as I go to my right, the alkaline levels increase. That means 14 is more alkaline than 8. 14 is more alkaline than 9. 14 is more alkaline than 10. 14 is more alkaline than 11. 14 is more alkaline than 12. 14 is more alkaline than 13. So that means the more I go to the right, the more the alkalinity levels increase. So that means if I notice that my solution has that dark blue coloring, it belongs to that pH of 14, and therefore it is highly alkaline. And then maybe if I get 10, you realize that it's shady blue. So that means in that case, we are still looking at a lower level in alkalinity. So let's go ahead and hear the video.
The closer to pH 0, the more acidic a solution is. The closer to pH 14, the more alkaline a solution is. Universal indicator is very versatile because it can show us how acidic or alkaline a solution is. The universal indicator colour chart corresponds with pH numbers, so it can help us to estimate the pH of a solution. A few drops are added to the solution, and the colour is matched with the colour chart, which indicates the approximate pH. If the solution turns red, it has a pH of 0, so is very acidic. If the solution turns green, it has a pH of 7, so it is neutral. Universal indicator paper works in a similar way. A clean glass rod is dipped into the solution, and 1 drop of solution is transferred to a piece of universal indicator paper on a white tile. After a short period of time, a colour will develop, which can be matched to the colour chart. Here, the paper has turned dark blue, which means the solution is alkaline because it has a pH of 11. Universal indicator colours vary slightly between manufacturer, so colour charts are usually provided by them. Summary. The pH scale is used to measure whether a solution is acidic, alkaline, or neutral. Indicators are dyes that change colour when added to acidic, alkaline, or neutral solutions. Universal indicator is a wide-range indicator that can tell us how acidic or alkaline a substance is. Solutions are more acidic if they are closer to pH 0, and more alkaline if they are closer to pH 14. pH 7 is neutral. Each pH number has a specific colour. This means that universal indicator can help us to estimate the pH of a solution. Acid, a solution with a pH less than 7. Alkali, a solution with a pH more than 7. Indicator, a substance used to determine if a solution is acidic or alkaline. Neutral, a solution with a pH of 7. pH scale, a scale to show how acidic, alkaline, or neutral a solution is. An acid has a pH between 0 and 6. An alkali has a pH between 8 and 14, and neutral solutions have a pH of 7. Universal indicator, a type of indicator that can tell how acidic or alkaline a solution is.
So that is briefly maybe how we can talk about a universal indicator. So you can take a screenshot and use those notes for your personal revision and include them in your notes. But then before we close off this video, I wanted to emphasize that when we are talking about pH, because someone may be wondering, what is pH? Why are they even mentioning pH all the time? So pH, as you can see, the symbol is small p, capital H. The P should always be small and the H is capital. So the full, though we don't usually use it, the full of pH is potential hydrogen. So when we are defining pH, we are basically, because when you look at that pH scale, it's basically telling us that there are solution substances that are alkaline, there are those that are neutral, and there are those that are acidic. So basically what we are looking at when we are looking at pH, we may define pH as the degree of acidity or alkalinity of a substance. So when you're looking at pH, you define it as the degree of acidity or alkalinity of a substance. Because when you look at that pH scale, it's containing the different figures in which we can determine the degree of acidity or the degree of alkalinity of a given substance. So basically that is what pH is. So are there any questions before we move on? Okay, so we are going to take a 5-minute break. It's 3:15, so that means by 3:20 we should resume our lesson. So don't log off. Stay on, just stretch a little for 5 minutes, and then we shall proceed.
Universal Indicator and the pH Scale by kscience.com. Imagine you have 3 colorless solutions, solution A, solution B, and solution C. How do you know which one is acidic, alkaline, or neutral. To know this information, we use indicators, which change color depending on the pH of the solution. We can use a pH scale to tell us how acidic, alkaline, or neutral a substance is. The pH scale is from 0 to 14 and is linked to colors. We can use universal indicator paper, which looks something like this, which is just paper soaked in universal indicator solution. When this universal indicator paper is dipped into the substance, the color change tells us if a substance is acidic, alkaline, or neutral. So if the color of the universal indicator paper is red, orange, or yellow, this tells us the pH is going to be between 0 to 6. This tells us the substance is an acid. Whereas if the color change is green, this tells us the pH is 7. And this tells us the solution is neutral. The solution is neither acidic or alkaline. And if the universal indicator paper is any color from blue to purple, this tells us the pH is from 8 to 14. So the solution is an alkali. It's question time. Attempt these questions to check your understanding. So to summarize what we've just learnt about the pH scale, if the pH is below 7, the solution is acidic. If the pH is 7, the solution is neutral. And if the pH is above 7, the solution is alkaline. If the pH is between 0 and 2, the universal indicator solution will be red. And the pH will be very low due to there being many hydrogen ions in the solution. Examples of acids with low pHs between 0 and 2 are hydrochloric acid and sulfuric acid. A solution with a pH of between 3 and 4 will cause universal indicator solution to be orange, and there will be less hydrogen ions dissolved in solution. Vinegar containing ethanoic acid is an example of a substance with a pH of between 3 and 4. A pH of 5 to 6 will cause universal indicator solution to turn yellow, as there are the lowest amount of hydrogen ions in solution. Black coffee and rainwater are examples of solutions which have a pH of between 5 and 6. A pH of 7 will cause universal indicator solution to be green. Pure water, which has a molecular formula of H2O, will cause universal indicator to be green. A neutral solution will have no hydrogen ions or hydroxide ions in excess. They will have all reacted to form water. A pH of 8 to 9 will cause universal indicator solution to be lighter blue. A pH of 8 to 9 will have few hydroxide ions in solution. And an example of this pH would be baking soda. A pH of 10 to 11 causes universal indicator solution to be dark blue and will have more hydroxide ions in solution compared to a pH of 8 to 9. An example of a pH of 10 to 11 could be washing powder. A pH of 12 to 14 causes universal indicator solution to be purple, and this has many hydroxide ions in solution. An example of this pH would be oven cleaner. It's question time. Attempt these questions to check your understanding. Although using universal indicator paper can be very effective, the problem is using colors can be very subjective. One person can say it has this pH, and another person can interpret the color as being a different pH. So an alternative is using a pH probe or pH meter, which gives you exact data on a digital display like this. This digital display is much more accurate, and the pH probe or pH meter can be connected to a data logger, which records pH changes accurately over time. We can then use a graph to interpret the data, where time is on the x-axis and pH is on the y-axis. Pause the video here to practice the keywords. The answers will follow. Press pause to answer the questions. The answers will follow. If stuck, just rewatch the video.
Okay, so welcome back from that break of 5 minutes. So I want us to play this video because it has some interesting questions that you may need to answer on a personal level. So as it plays, I'll be posing the questions, then make sure that you're able to answer. Share your answer in the chat such that I can take note of what your thought was.
kscience.com. Imagine you have 3 colorless solutions: solution A, solution B, and solution C. How do you know which one is acidic, alkaline, or neutral? To know this information, we use indicators, which change color depending on the pH of the solution. We can use a pH scale to tell us how acidic, alkaline, or neutral a substance is. The pH scale is from 0 to 14 and is linked to colors. We can use universal indicator paper, which looks something like this, which is just paper soaked in universal indicator solution. When this universal indicator paper is dipped into the substance, the color change tells us if a substance is acidic, alkaline, or neutral. So if the color of the universal indicator paper is red, orange, or yellow, this tells us the pH is going to be between 0 to 6. This tells us the substance is an acid. Whereas if the color change is green, this tells us the pH is 7. And this tells us the solution is neutral. The solution is neither acidic or alkaline. And if the universal indicator paper is any color from blue to purple, this tells us the pH is from 8 to 14. So the solution is an alkali. It's question time. Attempt these questions to check your understanding.
So the pH of 3 is more acidic than the pH of 4. What could that be? Is it true, false? Okay, I'm seeing someone saying it's true. That is very good.
So to summarize what we've just learnt about the pH scale, if the pH is below 7, the solution is acidic. If the pH is 7, the solution is neutral. And if the pH is above 7, the solution is alkaline. If the pH is between 0 and 2, the universal indicator solution will be red. And the pH will be very low due to there being many hydrogen ions in the solution. Examples of acids with low pHs between 0 and 2 are hydrochloric acids and sulfuric acids. A solution with a pH of between 3 and 4 will cause universal indicator solution to be orange, and there will be less hydrogen ions dissolved in solution. Vinegar containing ethanoic acids is an example of a substance with a pH of between 3 and 4. A pH of 5 to 6 will cause universal indicator solution to turn yellow, as there are the lowest amount of hydrogen ions in solution. Black coffee and rainwater are examples of solutions which have a pH of between 5 and 6. A pH of 7 will cause universal indicator solution to be green. Pure water, which has a molecular formula of H2O, will cause universal indicator to be green. A neutral solution will have no hydrogen ions or hydroxide ions in excess. They will have all reacted to form water. A pH of 8 to 9 will cause universal indicator solution to be lighter blue. A pH of 8 to 9 will have few hydroxide ions in solution, and an example of this pH would be baking soda. A pH of 10 to 11 causes universal indicator solution to be dark blue and will have more hydroxide ions in solution compared to a pH of 8 to 9. An example of a pH of 10 to 11 could be washing powder. A pH of 12 to 14 causes universal indicator solution to be purple, and this has many hydroxide ions in solution. An example of this pH would be oven cleaner. It's question time. Attempt these questions to check your understanding.
So what is our answer there? Acids have a pH 1 above 7, 2 of 7, then 3 below 7. Let's quickly share our thoughts in the chat such that we can move. I'll come saying below 7, and someone else is saying 3. The rest of us, please share your answers such that we know we are with you. Below 7, okay, bravo, that is good. So let's proceed. Then this one is saying a neutral solution has a color of dash on the pH scale, blue, red, and green. Is it 1, 2, or 3? Which one is the correct answer? Is it 3, green? Let the rest also share their thoughts. Green, green. Okay, bravo, that's good. You're doing an amazing job. Okay, let's move to the next question. A strongly alkaline solution has a color of dash on the pH scale, blue, red, or purple. Let me see those that were paying attention. Okay, I can see people are actually paying attention and probably making notes. This is good. So all of you are saying purple, at least those that have shared. That is good. Keep it up.
Although using universal indicator paper can be very effective, the problem is using colors can be very subjective. One person can say it has this pH, and another person can interpret the color as being a different pH. So an alternative is using a pH probe or pH meter, which gives you exact data on a digital display like this. This digital display is much more accurate, and the pH probe or pH meter can be connected to a data logger, which records pH changes accurately over time. We can then use a graph to interpret the data, where time is on the x-axis and pH is on the y-axis. Pause the video here to practice the keywords. The answer.
Okay, so we have these questions here. I'm going to give us just 1 minute to digest what the question is. And if you come up with the answers of the puzzle, just put up your hand and you share with us the whole puzzle. Don't just give us only one answer because it will be hard to track which answer goes where. So use 1 minute to digest the whole story and then put up your hand when you're ready to share and you tell us what your thoughts are. Okay, Marvel is saying the first word is universal. That is good. So let's have one person put up your hand. Tell us what you found out. Children of God, someone put up your hand and share with us. At least 1 minute is now done, and we've been watching this video together. So let me see some hands up. At least Marva has already given us a clue that the first word is universal. So that means universal indicator finds. Look, I'm seeing a hand here. 2 hands. Beautiful. Okay, let's see. Marvel. You can unmute, then we'll hear from Kion.
Sure. I'm sure only up to before contain. Yeah. So
That is okay.
the first one is universal. The second is color.
Marvel, briefly.
Yes,
Sorry
please.
for interjecting, but I think read the whole sentence such that it can make sense to those that are listening.
Oh, okay.
Thank you.
Universal indicator finds the pH of a solution using color. The pH scale is a scale which tells you how alkaline or acidic a solution is. 0 is the most 0 is the most acidic, 7 is neutral, and 14 is the most alkaline. Okay. Acidic solutions contain H plus H minus ions, so the pH is above 7. And okay, yeah, that's where I stopped.
After 14 is the most alkaline. That dash, what did you say? Okay, I think you had already mentioned because I didn't get that. That's why I haven't written it. But thank you so much, Marvel. That was good. Let's hear from Kion, then we'll hear from Samantha.
Universal indicator finds the pH of a solution using color. The pH scale is a scale which tells you how acidic or alkaline a solution is. 0 is the most acidic, 7 is neutral, and 14 is the most alkaline. Alkaline solutions contain H- ions, so the pH is above 7. Acidic solutions contain H+ ions, so the pH is below 7. A pH probe is electronic, so gives a very accurate and objective reading, and if attached to a computer, readings can be taken over. That's where I stop.
Okay, thank you so much. That is very good. I'm actually going to clap for all of you after writing this. Then let's hear from Matthew. Just briefly, let me first fill in this answer here. Okay, the rest of the hands went down. Yeah. Okay, so we still have Matthew's hand up. So let's hear from Matthew. Sorry, I made you. Please put up your hand again, Matthew. I lowered your hand instead of asking you to unmute. So if you still have the answer, you can re-raise your hand. Okay, thank you. You can unmute.
Universal indicator finds the pH of a solution using color. The pH scale is a scale which tells you how acidic or alkaline a solution is. 0 is the most acidic, 7 is neutral, and 14 is the most alkaline. Alkaline solutions contain OH negative ions, so the pH is above 7. Acidic solutions contain H ions, so the acidic is below 7. A pH probe is electronic, so gives a very accurate and objective reading, and if attached to a computer, reading can be taken over to a recorder and plotted in a graph.
Okay, thank you. Can be taken over a data recorder. That is very good. Samantha, I am coming. A data recorder and plotted in a graph. Okay, so thank you all for your submissions. That was wow, and I promise to clap for you. So a pH probe can also be called a pH meter. So if you feel the word probe is a bit somehow, you could use the word pH meter. They all do the same thing. So you realize that this is basically a summary of what this whole video was about. You have the universal indicator finds the pH of a solution using color. The pH scale is a scale which tells you how acidic or alkaline a solution is. 0 is the most acidic, 7 is neutral, and 14 is the most alkaline. So alkaline substances contain OH ions. Those are the hydroxide ions that he was talking about. So the hydroxide ions, because in our first lesson, if you go back and watch the video, you'll notice we say that alkalines are substances that give off hydroxide ions as the only negatively charged ions when dissolved in water. So that means their pH is above 7. Then for acidic solutions, they contain hydrogen ions. And still, when you go back to that recording, you'll notice that we say that hydrogen ions are the ones that actually make acids to be called acids, if that statement is right. So you find that without hydrogen ions, we can't have acids. So these hydrogen ions are the only positively charged ions when an acid is dissolved in water and the pH is below 7. So we use a pH probe or meter, which is electronic and gives an accurate and objective reading, and it is attached to a computer reading. And these readings can be taken over time. I want to believe that it's better than, because if you say it's attached to the computer here, already that is the data recorder, because the computer is the one reading off those data recorders. So this can be recorded over time, because you're going to have to plot a graph of time against pH. So that means you're going to have the readings taken over time and plotted in a graph. So that is very important. And according to your responses, at least I believe every one of us learned something.
This will follow. Press pause to answer the questions.
And to
The
just come
answers
back
will follow.
briefly such that we
If
look at those answers and we see if we were right.
Press pause to answer.
So you realize that we had the right answers in all those places. Because where you see the yellow, it's basically showing that those were the answers that were missing in that part. Okay, so I can continue.
Press pause to answer the questions. The answers will follow. If stuck.
So please take a screenshot of this. You'll answer those questions in your book. Just take a screenshot such that after the lesson you get your book, rest a bit, and then you work them out and see if you actually understood what the lesson was about. Please let me know in the chat when you're done taking the screenshot. I'll wait for only 3 people. Once they text they are done, then we'll move on. So if you finish taking the screenshot, just let me know in the chat. Okay, I've received at least 7. So that is good. That means all of us at least are done on average. So
Just rewatch the video. Press pause to go through your answers and make any corrections to your mistakes.
yeah, I'm
And
not
don't forget to
positive
visit
this is the best
kscience.com for
answer.
more videos, worksheets, and quizzes at kscience.com. And don't forget to like and subscribe.
Okay, so I hope you were able to learn something and also note down something from there. So basically, I think looking at that pH scale, we have now at least an idea on what strong acids are and what weak acids are, and what strong alkalis are and what weak alkalis are. So when we're looking at the strength of acids, especially those that we interact with in the lab, we have the strong acids that are actually very common. We have the hydrochloric acid, we have the sulfuric acid, and then we have the nitric acid. Then for the weak acids, we have the ethanoic acid, methanoic acid, and then carbonic acid. But of course, as we advance, those of us that will keep with the chemistry, you realize that you'll find out why we call these acids strong and why we call the other acids weak. But for now, just have an understanding that we have both the strong acids and the weak acids. So those are just a few examples, but of course you can find other examples, especially for the weak acids. For the strong acids, we may really circle around these 3, but for the weak acids, you'll find there are several of them that we can actually look at. So still when it comes to the alkalis, Donald, I'm coming. When we get to the alkalis, you notice that still, when you look at sodium hydroxide, it's higher in the degree of alkalinity compared to baking soda. So how are you going to know? Still, you go back to the pH scale. And among the strong alkalis, we have the sodium hydroxide, we have the potassium hydroxide. And the weak alkalis, these ones are actually very unique. We have only one. The rest can even fall under the strong alkalis, but we have only one weak alkali, and that is ammonium hydroxide. So like I said, still the chemistry of why we call them strong and weak, you go back to the pH scale and use the universal indicator. But the chemistry beyond that, you may need to grow more in the chemistry world. But for now, that is basically the information you need about weak and strong alkalis. Yes, Donald.
Because afraid I see
Donald, is
don't
that
talk.
why you unmuted? I thought you had a question. Okay. So let's continue. And so determination of pH, we've looked at this in the different videos. So at least by now we really know what to do or what to say. So these are the different corresponding pH values, the pH color changes of the different substances to help us really tell which pH is what substance. So you're going to take a screenshot of this table as well. this time round endeavor to share your answers on this table. Corresponding pH, that means if they say dilute hydrochloric acid, when the universal indicator was added to it, we got a red color change. What is the corresponding pH? So you're going to notice that the red was on 0. So that means the corresponding pH there is 0. So you're going to do your research or even rewatch this video later on when it's posted in the group, such that you can be able to tell which color falls under which pH, and you attempt that table and complete it. So just take a screenshot of this table and endeavor to complete it. Otherwise, I think we are going to stop here today and we'll begin from there next week. Unless anyone has a question, I would want to close the lesson at that. And I hope you learned something and noted down a few things that you'll read after this lesson, because it's always important to note down something such that when you go to make research, it's easy for you to synchronize the notes. And I also want to encourage that much as ChatGTP is good for information, you should be able to pull out what is important, because some of us we pick everything the way it is and then we post the answer there, not remembering that when you're in an exam, ChatGTP will not be there. So when you go to ChatGPT, read through the work that is presented and also use other sources, especially textbooks, because they will have the right information at all times. Because ChatGTP, if you subscribe to it, you can actually also post your answer, whether it's true or false. It will always give us those answers. The same thing with Google. But when you're using a textbook, you become more authentic. I know we are in a digital world, but we cannot underemphasize the importance of textbooks. So it's very important that you have various sources such that your information is well packaged. So that is it. Since there are no questions, have a lovely weekend. Thank you for attending the lesson. God bless you.